वेलकम बैक टू माय चैनल फिजिक्स लवर। आप देख रहे हैं कोवेरिएंट डेरिवेटिव ऑफ कॉन्ट्रावेरिएंट टेंसर। आज हम इस लेक्चर में पूरा डिस्कस करेंगे। बिफोर डूइंग दिस डेरिवेशन, फर्स्ट वी नो अबाउट द व्हाट इज द metric tensor and the covariant basis vector as well as the contravariant basis vector. That's why first I discuss over here is what is the metric tensor. Metric tensor is a fundamental tensor and it is denoted by this Gij and it is given by the Ei.ej, where Ei is equals to del r upon del qi and Ej is equals to del r upon del qj. Here, and this is r is in the point space in a vector. The position of a vector of a point in the space is r. That's why this is the our Gij. The covariant basis vector are defined as the, from this we discuss about the covariant basis vector. Covariant basis vector, and this is the Ei is equals to del r upon del qi, which is equals to del x alpha divided by del qi times E alpha. This is our unit vector. This is for the 3-dimensional and this is for the 1-dimensional, and Ej is also del r upon del qj, which is equals to del x alpha divided by del q. Here is in indices is j, that's why it is a j and E alpha. These are the our covariant basis vector. And now in case of the metric tensor, multiplication of these two basis vector is a covariant metric tensor. In case of the contravariant metric tensor, in case of contravariant, in case of the contravariant basis, it is written as powers, and epsilon j is equals to del qj divided by del x alpha, and E alpha is the unit vector. This is the our equation 2. Let's say this is the our equation 1. Before doing this covariant derivative of contravariant tensor, we must know about these things. Otherwise, we can do this derivation. Let's start about the our topic. Our topic is the covariant derivative of contravariant tensor. Also, as we know, what is the covariant tensor and covariant tensor and the contravariant tensor. First, you have to know about these two tensor, which was I already discussed in the previous video. Now, from the transformation law, the transformation law, the contravariant tensor is given by this del x I upon del q j times a. This is our equation 1 for this derivation. This is differentiated with respect to any qk or qm, as you like. I differentiate this equation 1 with respect to qk, differentiating equation 1 with respect to qk. And now this is partially differentiating del ai upon del qk, which is equal to del xi upon del qj as a adjective, and differentiating this delta j upon del qk plus, and then again del squared xi upon del qj del qk times aj. Here we differentiating this equation 1 with respect to qk. In the vector form, or in case of the covariant and the contravariant basis, we write in the vector form. In the vector form, del bar of I upon del qk is equals to, here's this term, and this term is similar as the this term. That's why I write this is by this equation over here. We get the delta aj upon del qk is plus aj and delta ej upon del qk. This is our equation 2. Now also we have covariant metric tensor. Covariant metric tensor. ei dot ej is equals to gij is our covariant metric tensor. Differentiating this covariant metric tensor with respect to qk again. Differentiating, this is equation 2 with respect to qk again, we get ei delta ej upon del qk plus delta ei upon del qk dot ej equals to del qij upon del qk. From the Christopher's second symbol, we write this is equals to jk of I plus ikj, which is equals to del gij, ji or ij divided by del qk. Here's jk of I is equals to ei delta ej upon del qk. This is the Christoffel second kind of symbol. That's why from there, if we arranging these two, we get the ei jki is equals to delta ej upon del qk. This is ei, which is transformed into this form. It is in base form, it is in power form. Actually here jki upon ei, which is 1 by ei, is equal to this. Okay, that's why again we have delta ej upon del qk, which is equals to gil el jk of I. This is actually come from the Christoffel second symbol. Here ll is cancelled, and which is equals to exactly this ei, and this is jki, and the right hand side is over here, which is denoted by the ELLJK. Let's say this is equation number 3. And then we have from equation 1 and 3. From equation 1 and 3, del A by del QK is equals to delta Az upon del QK EJ plus AJ EL LJK. Here doing about the this is our equation 2, and from there this is equation 2, sorry, and this is 2a, and this is 3, and we put the values of delta EJ upon del QK, and by using the equation 3. Nothing doing here. We need this term. To calculate this term, we use the covariant metric tensor, because of here is a delta EJ is in the base. That's why we calculate this is here. Now this LJK is a Christoffel symbol of second kind. Now interchanging the domain indices J by L in the final term. In this term, we changing the domain indices. This is interchanging the domain indices in the final term. Domain indices J and L in the final term, because of we have to take the common EJ from there. If we put the L equals to J, and EJ will be common there. That's why we interchanging the variable, and del A by del QK, there is a something is missing. Here is from this equation, we use this equation. This is over I, and also where there is I, which is equals to delta Az upon del QK plus AL JLK, and EJ is common, which is written in the vector form is the JK in this form, and this is also EJ. Here this AJK is a mixed tensor of rank 2, क्योंकि here is दो indices है, mixed tensor of rank 2, and this is the DAI upon DQK is equals to AJK times EJ. From there, DAI is equals to A DQK times EJ. This is our required expression for the contravariant tensor, where we do the covariant derivative of contravariant tensor. Please like, subscribe my videos. Thank you for watching, and keep supporting and loving.